Hey everyone, so in this video we want to talk a bit more about collisions because we looked at relatively simple cases so far, but collisions are some problem that you will always have to face, and especially beginners are always surprised about this. But this is important for the whole course and your career, theoretically, because this is not only true for POPs but for everything. So let's look at a couple of cases we need to understand. So let's start with something simple, and that is when you use the surface representation, not the SDF representation, you will notice something. So currently we have here this little parkour and a couple of points that fall into this little shape there. And when we look from the side with space 3 and I press start, I can see that when I go close, here there's a little bit of bouncing going on, but down here you can see it better, that the points are perfectly on the surface. And this is because the internal SDF that we just saw will make sure that it calculates the points to that position. Before we move on, actually a quick note about the points. You can see the points do not stack up. They do not fill a volume or anything. That is because in a POP simulation, points do not collide with each other. This is something we will talk later on about in a separate chapter called grains. If you need the points to collide and maybe fill a volume or something, then look into the grains chapter. But in a normal POP simulation, there's no collision between the points. Just keep that in mind. Now, let's say we don't want to use SDFs as the representation because, for example, this rough result here in the collision actually comes from the fact that this is an SDF. So let's switch this to from a volume representation to a surface collision and visualize that. And if I start this now, you can see that the collision is much more precise, so to say, down here as well. But there's one problem here, and that is obviously there's a big gap now between my collision object and the points. Where does that come from? Well, as we talked about in the SDF video, as soon as you calculate collisions with a completely thin surface, which the surface collision is, it only calculates the surface, it considers the objects as hollow, then you can't calculate an exact collision. You have to kind of assume a certain area, a buffer space where a collision is considered a collision. And this is currently what we see. And this thickness, so to say, is actually the size of the points in form of the attribute p-scale. Now, if you look at the setup, we actually don't have a p-scale attribute either before nor after the simulation or in the simulation. There is no p-scale attribute. And in this case, actually, it calculates its own default p-scale, and we have to overwrite this. So what you can actually do, even on the volume, interestingly enough, you can set the p-scale as an attribute in your source object. So we set the p-scale, and this is actually here the default p-scale that Houdini usually calculates, 001. So if I run this now, we shouldn't see a difference because it's the same as before, only that now we define the p-scale ourselves. So to prove that to you, let's lower this to 001. And if I run this again, you can see now that the distance is much smaller and it's almost on the surface. But if we go close enough, you can see, of course, there's still a gap in here and you will never get rid of that. It's always a gap of this size in meters. So it depends, of course, on your case and your camera, what makes sense to you. So it will never be 0, but you can set a number that makes sense in your case. So keep that in mind. P-scale is something you will need when you use the surface collision. And not only is it actually the p-scale, it's also here the collision radius that you can define for the object itself. I'll leave it at 0 for now, but this could be something you can change as well if the point scale doesn't work. Now an example when you need a surface collision representation is this, for example. So this is a pretty complex shape here. And as you can see, I use the surface representation here to get the right result to collide with my points. Because when I try to turn this complex shape into an SDF, which of course was the default, then you run into a problem. The default divisions are not even enough to see the wings of this rotor. So let's increase that maybe to 100, and you can see it's still missing a lot. So let's go even higher, even though I said around 100 I would start to really question my approach. And here you can see I have to go up to something like 250 to get a reasonable representation of this shape. And this can be really problematic and slow. So here is a case, because of the complexity, where I would actually go with a surface representation instead. And we will see in a second that sometimes you really have to do that no matter what. But this is actually not what I wanted to talk about in this example. What I wanted to show you is this rotor is actually moving outside. So I put an animation on this. Now, the weird thing is when you have any kind of animation or movement, then in the DOP.NET, when you just put it in via a static object, you will not see that movement. Now, this is easy to solve actually. In the static object, there's a use deforming geometry checkbox right at the top. And if you turn this on, the whole thing now is moving just like the animation from outside. So this setting really just means, you know, take the animation from the outside and apply it to my simulation. So that was relatively easy. Let's talk again more about the surface stuff. And here's an example of, especially as a beginner, where you might be surprised that this is a problem. What I built here is a very simple, you know, wooden structure with a couple of planks that I then copied with a copy and transform, and then, you know, turned into some kind of a weird object. And when I try to simulate that, and by the way, it's rotating. And if I try to put this into my simulation as a static object, and of course I set use deforming geometry to on, and you can see it moves, so that part is working, but the collision is a mess. Now, of course we know why, probably because the default volume representation is probably not very good, and it isn't. Okay, fair enough. So let's increase that. But even with 120, you can see there are still holes in it, and the result is, you know, really problematic. And you can see here, it doesn't work. Now, okay, maybe I have to just increase that number to, you know, this insane thing that we had before, maybe 250. And now you can see it becomes really, really slow. And if I actually do this to myself and check the result, which takes absolutely ages. So give me a second to actually simulate this. So after a few very painful minutes, you can see it still doesn't really hold up properly. It's definitely better than before, but here you can see there's still a lot of points falling through. So this is not the solution. Well, okay, well then let's get rid of the SDF solution here. And we take the surface collisions. And this actually works much, much better, but actually there's still a few errors. Now, you know, that might not bother you too much, but here you can see 2 points are falling through, even though they shouldn't. So even a surface collision can sometimes create problems. I mean, to be fair, the solution here is probably to increase the substeps either outside or here on the pop solver. Outside is probably the easiest, and then it should definitely work. There, now they're gone. So sometimes you have to increase the substeps when working with surface collisions. But let's say for some reason you don't want to use surface collisions. And here's an example. If you have a complex version of this geometry, like this with a lot of points, and maybe this is because, you know, you get this from somewhere else, from the modeling department or something, which is the same, just with way more geometry, then you run into the problem that your surface collisions are also very, very slow because, well, it seems already slow, but wait a second until the collision is happening. There you go. It becomes super slow because now the collision has to be calculated for way more geometry. And as you can see here, it also doesn't solve actually the problem. If the geometry is too complex, it breaks apart. And what I want to show you with this example is that sometimes it makes sense to simplify your geometry. So this complex geometry can actually be represented by something much simpler. And that is, for example, I take all this and, for example, with a bound node, I just turn this into a box. And then I use this as my representation. Sure, it's not the same object, but for the collision, it might be fine. And even if I don't use surface collisions, which will work for sure, but let's say I turn this back into my SDF representation, even with a lower resolution, you can see that the simulation now is fast and very accurate. And because this is so common that we can simplify geometry massively, this is even an option here in the static object. So here you can switch actually to something like implicit box or implicit sphere and stuff like that. It doesn't work in our case because it's moving and this only takes the whole scale, but it's an interesting thing to keep in mind that massively simplifying your geometry purely for the collision part can make a lot of sense. And if we look at the result and we combine it not with the representation for our collision, but we create a separate version of this purely for rendering and combine those, you can see that from a right angle, nobody will see that something is wrong here. So nobody will see that this is not actually the right representation of this object, but you have a fast feedback and the right result without much hassle. So keep that in mind. Sometimes you have to put a bit of love into simplifying your collision objects. So another very common thing is when you try to turn an object into an SDF for collisions, you will sometimes run into problems if it's not watertight. So what I mean by that is that this object here looks perfectly fine, but if I try to turn it into an SDF, for example with a VDB from polygons, then I can see there's something odd with it. And it's not a question of the resolution here. If I lower this, it's still broken. You can see it only creates dots. And the reason is that it's actually open at the bottom. So what I usually do here is a polyfill, which finds all the holes and fills it. And in this case, it works fine because it's set to quadrilaterals, horrible word, but basically that means quads. And in this case, it works, but what will always work no matter what is if you set it to triangles, which I usually do, because then I can be sure that every hole will be filled. And then turning this into an SDF is no problem anymore whatsoever. Now, to be fair, if I would have taken my geometry directly into my PopNet, you can see that the static object can actually handle this. So the static object nowadays became much better. I think side effects improved the quality of the node so that it can actually handle non-watertight objects very often. But nonetheless, if you have problems with it, then keep in mind a simple polyfill should help you out, and then the problem is solved for sure. And in the same vein, sometimes people download geometry from the internet, and there's absolutely nothing wrong with that. I do this too, but be careful what you download there. So for example, we have a bucket here, and when we run this, those points falling into this bucket, we run into this horrible mess. Now, this is because the geometry might look good at first glance, but you might already be able to see it. This is actually a horrible model. And very often what you have is models that are actually made for real-time engines. So the main goal here is to lower the poly count, and the results in the topology are that those are completely broken. So what happened here for some reason, someone didn't properly delete the faces on the top, but only you kind of made the connections disappear, but the points are still there. So this is completely broken and utterly useless. And I actually even tried to fix that and I wasn't able to. So sometimes you have models that are just not made to be used in simulations. And this is a good example. In this case, I would recommend kind of rebuilding this thing from scratch or just use another model. So this, for example, is clearly not made for real-time engines. And this is better suited for this because it doesn't have holes, it doesn't have broken geometry. And when you use this instead as a collision object, then you can see you don't run into any problems. So my point here is not every geometry can be used. And if you run into a case where you can't use it at all, then this is just sometimes a bad luck. And you might have to rebuild the model. And then finally, let's say you have a model but you need a relatively high resolution to represent the surface detail. And what I have here is an SDF that is calculated with 200 divisions in the max axis. Everything works, but of course, since this is, and I forgot to say that, this is actually animated. So if I look at this, this is for some reason rotating. That means, sure, I can activate the deformed deforming geometry here, but what this results in is that the SDF has to be recalculated every frame. And you can see how slow that is. That takes a lot of work. Now, if for some reason you really need this, and this can absolutely happen, then there is a good trick to speed this up, and that is not to rely on the DOPNet to calculate your SDF for you, but simply do this before you bring it in. So you calculate an SDF with a simple VDB from polygons, which is as slow as we've just seen. It takes a while to calculate this for a complex shape, but you just cache this out and bring it back in, and then it reads in the result. And you can use this actually directly. So this is not a geometry, but an SDF, of course, as we can see. You just have to make sure that in the static object, and this is very important, otherwise the trick doesn't work, you have to change the settings here under volume to volume sample. By default, it's set to ray intersect, and this will actually still work as long as you have a good number here, because then it will still calculate the SDF every single time again. So be careful here. You have to switch this to volume sample. So basically it means sample the volume from outside. And to make sure that this actually works, just set the uniform divisions to 1 or something. And if it's still intact, then your trick worked. And when you start this, you can see it's much, much faster, because now the simulation doesn't have to calculate the SDF every single time itself. It just reads the already done SDF from outside. And this is a much quicker solution, especially for complex shapes. Just remember to set the mode to volume sample, and then this trick works. Okay, so those are a couple of tricks about collision geometry. I hope this is helpful. Thanks very much and see you later. Cheers.